Hello, good afternoon. I'm Jingwei from National University of Singapore, and today I'm very glad to be here presenting our work, Beat Transformer, Demixed beat and downbeat tracking with dilated self-attention. So, music audio beat tracking is a well-established MIR task, the goal of which is to infer beat and downbeat activation from an input audio spectrogram. So in this work, our intuition is that when a human tracks music beats, instead of relying solely on the spectral energy, we usually have a deeper musical understanding about the musical context. And such context in turn can help us track music beats in an easier and better way. To reflect our musical understanding in the model, one of our key proposal is demixed beat tracking. Basically, we use splitter to demix an audio mixture into 5 separate instrumental channels. And this demixed representation is then sent to a transformer model with both time-wise attention and instrument-wise attention. To model time-wise attention, we introduce a dilated self-attention mechanism, short as DSA. Basically, we compute self-tension only within a short window, and when the layer goes deeper, the window dilates itself at a rate exponentially increasing itself. So here, as you can see, we have a dilated window of length 5, which is very short. In other words, each position can only attend to its neighbors, which are covered by the attention by the dilated window, so that the attention matrix is very sparse. To compute this sparse attention more efficiently, we introduce a rolling strategy. This strategy helps us to calculate self-attention only between the positions which are attainable. Conceptually, this technique is similar to the skew operation in music transformer, and we only require linear complexity to compute DSA, which is a huge benefit to our model training. Now recall that our model input have demixed channels, and for each demixed instrument channel, we use a temporal transformer layer with DSA to aggregate the information through time. And across the instrument channels, we use a instrumental transformer layer to aggregate frequency information. And here, a stack of 2 types of transformers form a demixed transformer block, which is the key component of our model. So here is an overview of our model architecture. As you can see, we use a total of 9 temporal transformer layers with DSA, and the middle 3 of which are expanded to demixed transformer blocks. We also introduced 2 ablation architectures. The first one is a non-demixed model, and in the second model, we replace the temporal transformer layer as a TCN layer. Essentially, we want to compare dilated self-attention with dilated convolution. In our experiments, we can first see that our model outperforms the non-demixed model with a good margin, especially for the downbeat tracking task. We can also see that our model performs generally better than the TCN demixed model, especially on the test-only GTZan dataset. We also introduced a partial demixed augmentation strategy, which yields a consistently better performance, which are also compatible with SOTA models, including Boch et al., the famous MadMom, and Hahn et al., which is basically a time frequency transformer architecture. And finally, we also visualized the dilated self-attention across the layers, and we found some pattern very interesting. For example, here in layer 3, we can see that the attention are typically aligned with the beat positions. And on layer 5, we can see a similar pattern, but this time aligned with the downbeat positions. This indicates that our model can gather information from different scales with an organized hierarchy, which also makes musical sense. So that is all of our work. I've already uploaded our code to our Colab notebook, and please feel free to have a check. Thank you.